All right. Can you guys hear me?
Yes.
Excellent. Thank you. All right. Today I want to talk mostly about microkernels. But first, a little bit of context to sort of help explain why people explored microkernels in the first place. People got the microkernels by trying to think about a little more broadly about what kernels should actually do. Like with XV6, it sort of does the things that Unix does, and we kind of take that set of abstractions and system calls and sort of facilities inside the kernel is kind of for granted as the target of what we're trying to design. But it's totally worth wondering, gosh, what should a kernel do in the first place? Maybe the particular kind of stuff that XV6 or Linux does is not really the best answer, or maybe it is. And of course, we're on somewhat treacherous ground here because now what kernels are is kind of a development platform for programmers. As we know, different people have like very different sort of subjective preferences about what kind of infrastructure they like to program on. So we can't necessarily expect a single best answer. But we can expect to maybe learn something and maybe make some progress by trying to think about what answers might be. So first of all, let me try to kind of crystallize what the traditional approach is to what kind of kernel interfaces we ought to be using. And Linux and Unix and XV6 are all examples of what I personally call a traditional design approach. But another word for it that kind of summarizes what this approach has ended up like is monolithic. Monolithic. And what that means is that the kernel is a single big program that does all kinds of things all within the same program. And indeed, this really reflects the way people thought about what kernels ought to be doing. A real hallmark of kernels like Linux is that they provide powerful abstractions. They choose things like file systems, which is really a complicated item. And they present file systems and files and directories and file descriptors as their interface, rather than, for example, presenting disk hardware as their interface to applications. So, and presenting powerful abstractions instead of very low-level abstractions has some big advantages. So these monolithic kernels often have sort of big abstractions. Like the file system. One advantage of big abstractions is that they're often portable. Of files and directories, you can implement files and directories on all kinds of storage. And you can use files and directories without having to worry about what brand of disk drive it's running on, or maybe it's an SSD instead of a hard drive, or maybe it's a network file system. It all has the same interface because the file system interface is pretty high level, pretty abstract. So an advantage of this is that it's a way to get portability. You can write an application and have it run on all kinds of different hardware without having to modify the application. Another example of this is that Linux provides an address space abstraction rather than providing direct access to the MMU hardware. And that's useful for portability and to sort of hide complexity from applications. So another big advantage here, these powerful abstractions, is that they tend to hide complexity from applications. So for example, the file descriptor interface that XV6 provides, it's a very simple interface, but just read and write on file descriptors can get much simpler. But behind it is some very complicated code for actually reading and writing the file system on disk. And so that's nice for programmers, but it makes for a big complex kernel. These big abstractions also help the kernel manage and share resources. We sort of delegated to the kernel things like memory management. The kernel keeps track of what memory is free. We similarly the kernel keeps track of what parts of the disk are free and what parts of the disk are in current use. So programs don't get to think about it. And that, again, it simplifies programs. It also helps with robustness and security even, because if programs were allowed to decide what parts of the disk are free or not, then maybe one program could use part of the disk that's already being used by another program. So the fact that the kernel is in charge of resource management helps with sharing and helps with security. But again, it's a force that sort of causes the kernel to be big. So anyway, so having the kernel be in charge of all these sort of juicy abstractions that even if they have simple interfaces, have a lot of complexity inside, have led kernels to be big and complex items. And another aspect of this monolithic design approach is that because it's all one program, all the different kernel systems, like the file system and the memory allocator and the scheduler and the virtual memory system, they're all part of one big integrated program. It means that they can peer into each other's data structures. And so that's just tended to make it much easier to implement facilities that are sort of parts of more than one, or what you might think of as more than one kind of module or subsystem. So for example, a system called like exec has its fingers deeply into the file system because it's reading binary images off the disk in order to load them into memory. It also has its fingers into the memory allocation and virtual memory paging system because it needs to set up the address space of the new process. But it's really easy. There's no problem with doing that in x86 or Linux because all the file system is right there in the same kernel program, and the virtual memory system is also right there as part of the same program. And if somehow there was some rigid split between the file system and the virtual memory system, it'd be much harder to implement something like exec that has sort of fingers in both of these pies. But in a monolithic system, just one big program, it's much easier. Another thing that makes implementing software inside a monolithic kernel like x86 or Linux easy is that all the code runs with full hardware privileges. All of x86 runs in supervisor mode, for example, which means there's no limits, there's no irritating, oh, you can't, read or write that memory here because you don't have enough privilege. All the kernel code runs with sort of maximum privilege. And the same is true of operating systems like Linux. So this design strategy is very convenient for kernel developers, and it's made it easy to build these big abstractions which are convenient for application developers. However, there's also a certain amount to criticize with the traditional monolithic approach. And this is starting to be part of the motivation for looking at other architectures like microkernels. So you might ask, why not monolithic kernels? So one is just that they're big and complex. So anything that's, Linux is, depending on how you count, Linux is somewhere between many hundreds of thousands and a few million lines of code. And people really do take advantage of the fact that one part of Linux can sort of look at the data of another, and that makes the programming easier. But it also makes there be a lot of sort of interconnections and interrelationships between code. And so it can be a bit challenging sometimes to look at Linux kernel code and figure out what it's up to. And anytime you get big programs, especially ones that are complex structure, you get bugs. And operating system kernels are no exceptions. And over the years, they've had all kinds of bugs, including bugs that are exploitable for security. So this is sort of a troubling set of relationships. If you allow a big monolithic kernel, you almost certainly can't avoid bugs and exploitable security problems. And that's a real, that really is a problem. Another reason why people are maybe not entirely happy with monolithic kernels is that they tend to just grow with all desirable features over time. And so, Linux is used for all kinds of different things, from telephone handsets to desktop workstations and laptops to tablets to servers on the internet to routers. And that's caused Linux, it's fantastic that Linux can support all those things, but it has caused it to be very general. So it has support in there for many, many different things. And any one application, like me running my web server, is unlikely to need, for example, Linux's very sophisticated sound card support. So there's just a huge amount of stuff that's there to allow Linux to be general purpose, which is good. But there's a worry that general purpose is going to tend to mean slow. That it may be good for all kinds of different things, but maybe not optimum for anything in particular. So it's very hard to, when you're trying to make something run really fast, it's great to have it just only do one or two things, so you can focus on optimizing a single code path. But if your software needs to do any one of 1,000 different things, it's much harder to have focused optimization. So Linux is not necessarily slow, but it's, you might wonder if it's really as fast as it could possibly be for any given situation. And so if you think about, if you think about almost anything in Linux or XV6, you may wonder whether it really needs to do everything it does. So for example, if you write a single byte over a pipe from one process to another, boy, there's a lot of instructions that get executed, even in XV6, which is a simple kernel, right? There's buffering, there's locking, could be a sleep and a wake up during a pipe read and write. There's maybe a scheduling, may call to the scheduler or context switch. That's a lot of stuff that's maybe not necessarily the absolute minimum that would be required to move a byte from one process to another. Another potential problem with these big kernels is that because they're so big and they sort of intentionally bite off some very sophisticated abstractions, they tend to have a lot of design decisions kind of baked into the kernel. So, in ways that you can't, even if you disagree with them, you can't really, tough luck. Like applications just have to live with it. So, as opposed to, in some fantasy world, maybe the applications could make a lot more of the decisions. So, some examples of things where you may be bummed out by the way the API is designed. For example, in Unix, you can wait for a process of your own children. If you fork, you can then wait for your children, but you can't wait for some other process. And maybe you want to wait for a grandchild or an unrelated process, but that's just not an option. It's just not the way things work, even if it would be convenient for you. Maybe you want to change the way another process's address space is set up. Maybe call mmap on behalf of another process that you're controlling. But again, that's just not an option. You can mmap, change your own address space, but not change other processes' address space. Maybe you're a database and you have B-tree indexes on the disk, and you may know a lot about it, the fastest way to lay out a B-tree on a disk. But if you're reading and writing files with the file system has no idea that you're actually writing a B-tree or how a B-tree ought to be laid out on a disk for fastest access. And so if you're a database, you're going to be kind of bummed. Maybe you're happy that you have this file system at your disposal, but it doesn't really do what you want it to do. And that's the sense in which design decisions are often baked into big kernels. And finally, a specific sort of issue that sort of came up in a big way in the 1990s, probably, was the notion of extensibility. That it might be desirable for programs to be able to change the kernel on the fly, like to be able to download new code into the kernel or change the way it operates or something, in order to do things like have databases be able to control the layout of data on the disk. And at least in decades past, monolithic kernels tended not to have any particular features that helped with this kind of extensibility. You're just stuck with whatever the kernel did. Okay, so these were sort of problems in the back of people's minds that led them to think about other kinds of, other ways of designing, other architectures for operating systems. And there were a number of ideas, some quite radically different, that people pursued. We're going to talk about one of them, a particularly popular one today, and that's the idea of microkernels. Microkernels, although many of the ideas go back to the beginning of computer history, they became a sort of hot research topic starting in maybe the mid to late 1980s. And the big idea, microkernel, this word, by the way, refers to a sort of general approach or concept. It doesn't refer to any specific artifact. There were many people who designed and built operating systems that followed the general sort of plan for microkernels, but each of these projects ended up designing an operating system that was maybe quite different from the others. So the key idea was the tiny kernel that supported just IPC, or inter-process communication, and some sort of notion of threads or tasks. So you have a kernel that provides you a notion of sort of process-like abstraction and a way for processes to communicate with each other with this inter-process communication, and nothing else. And everything else you might want to do, like have a file system, you'd implement as a process, as a task, as a user-level code, not in the kernel at all. So a picture for that might be, now we're going to use mu for microkernel. We've got the microkernel down here, and we got user space processes up here, and we might have all the kind of usual processes run. Maybe we're going to run VI, my favorite text editor, and my compiler, my Windows system. But also up here, as user level processes, we're going to have the file system, just as a server process in user space. Maybe we're going to have a disk driver that knows how to talk to my disk hardware. Maybe we'll have a network stack that knows how to talk TCP to my network interface card. Maybe we'll have a user level process that's in charge of doing fancy paging tricks, like memory mapped files, or maybe implements copy and write fork or something. And when my text editor needs to read a file, it needs to talk to the file system. And so it's going to send a message via IPC, inter-process communication, to the file system server, which has all the file system code in it, knows about files and directories. And the file system with server code may need to talk to the disk, so it might send another sort of disk read or write to another IPC to the disk driver, which somehow talks to the disk hardware. And the disk driver may return a disk block to the file server. After it does its thing, maybe the file server finally returns the data you asked for, again by inter-process communication messages, back to my text editor. But the critical thing to notice here is that the only stuff going down here in the kernel is support for these processes or tasks or threads or whatever they might be, and support for the inter-process communication message passing, and nothing else. There's no file system down here. There's no device drivers necessarily down here in the kernel. There's no network stack. All that stuff is up here as more or less ordinary user level processes. And so it leads you to a very small kernel with relatively little code to optimize. Like you can optimize IPC and there's not much else going on. And so this is the kind of picture we're going to talk about for the rest of the lecture. And just to give you a taste of kind of where this ended up, there are actually still microkernels in use today. And indeed, the L4 microkernel, which is the topic of today's paper, turns out to be used. There's many instances of L4 running because it's used in a lot of cell phones in the little microcontrollers that control the cell phone radios. And it's also apparently used in recent iPhones as the operating system that runs on the special dedicated enclave processor in the iPhone that hides the secret cryptographic keys. So there's a bunch of embedded, where these microkernels have won out is in little embedded specialized computer systems, not laptops, but computers sort of dedicated to single specialized tasks, where you may not need the complexity of Linux, but you do need some operating system. And the other thing that's the other sort of final result from microkernels is that the idea of user level services with other programs talking to them with IPC, that also has made its way into a lot of operating systems like Mac OS, which I'm running right now to talk to you. It's a sort of, as well as being a kind of ordinary monolithic kernel, it also has good support for user level services and IPC between Unix processes to talk to these services. So that idea also was a successful idea and widely adopted. Okay, so this is the basic architecture. I'm going to go on and sort of talk about some ways and reasons why this might be attractive. But first, are there any just kind of high-level questions about what it is I mean by microkernel? Okay. So what is it that people were hoping for when they started building microkernels? So one big motivation, although you wouldn't necessarily see it written down much, is just a sense of aesthetics, right? I think just a lot of people feel that huge, complicated single programs like a Linux kernel are just not very elegant. That surely we can build something that's much more, much smaller, has a much more focused design, isn't such a huge grab bag of random different features. So I think there was a strong sort of aesthetic feeling that surely we can do better than big kernels. But other sort of more specific things that you might be able to quantify are a kernel that's small might be more secure. Right? The fewer lines of code you have, probably the fewer bugs you have, less chance of somebody be able to exploit one of those bugs to break security. And in the extreme of that, you could imagine an operating system that's actually provably correct, where somebody can sit down and write a proof that the operating system has no bugs, or it does exactly what it's supposed to do and nothing else. And indeed, there is at least one verified, proved correct, proved secure operating system named SEL4, which is one of the many descendants of the L4 microkernel that from today's paper. But you really, people know how to verify sort of small to medium-sized programs, but they don't know how to verify huge programs. And thus the fact that microkernels are small is sort of a critical ingredient in being able to prove they're correct. Another reason why you might like small is that a small amount of code is often a lot easier to optimize than a huge program. Another reason why small might result in fast is that you don't have to pay for a lot of features that you don't use. If your microkernel does hardly anything, then you're not paying for a lot of features you're not using. Another reason for small is that a small kernel probably bakes in far fewer design decisions, forces fewer design decisions on application writers. And so it leaves them maybe leaves them more flexibility to make their own design decisions. So by the way, these are not necessary consequences of the microkernel approach. These are things that people hoped for and tried to achieve by using microkernels. Another set of reasons why microkernels seemed attractive has to do with the fact that a lot of the code was at user level. That is, a lot of features and functions that we sort of have grown used to being inside the kernel were actually user level services. So they hope that by sort of breaking the kernel apart and running the different parts, like user level services like a file service, file service server. It might cause the code to be more modular. It might sort of encourage operating system designers to split up all these functions into many separate services, and that might be a good thing. User level code is also possibly easier to modify. If stuff's at user level, it's usually easier to tweak it or replace it or modify it than doing the same stuff in the kernel. So maybe it's easier to customize. Putting the operating systems at user level also might make them more robust. If the kernel, something goes wrong with the kernel, usually you have to panic and reboot because you can't necessarily trust what's in the kernel anymore if it's had some bug that maybe causes it to overwrite a random part of its data. Whereas if you have a bunch of user level services and one of them malfunctions and divides by 0 or dereferences a wild pointer, maybe only that one server will crash and leaving the rest of the operating system intact, and maybe you can restart it, just that one server. So maybe user level, moving OS functionality to user level processes might lead to more robustness. And this is probably particularly evident for drivers. Most bugs in the kernel are actually in hardware device drivers. If we can manage to move the device drivers out of the kernel, then we might have many fewer bugs and crashes in the kernel. And a final advantage that people were thinking about back then is that you could emulate or run multiple operating system personalities on top of a microkernel. So even though the microkernel does hardly anything for you directly, you might be able to run a Unix server or something on top of it, maybe more than one on the same machine. And of course, that's what today's paper is about, is running Linux as a service on a microkernel. So these were all the set of things that people were hoping to be able to get some traction on by looking into microkernel designs. Of course, there's some sort of puzzles you have to think through, some challenges. One challenge, if you want to design your own microkernel, is actually figuring out, you want the API, you want the microkernel system call interface to be as simple as possible, because the whole point was to keep it small. Now, what is the actual smallest set of useful system calls you can get away with? And what does it look like? So that's not particularly clear. So we're looking at the minimum system call API. You need this minimum system call API. It's great if it's simple, but you actually have to be able to build some pretty sophisticated features out of your minimum system call API, because even if the kernel doesn't do much, in the end, you got to be able to run programs. You got to, maybe if you're trying to run Unix on top of a microkernel, you got to be able to do things like fork and mmap. So as part of the system call interface, simple, low-level system call interface, it has to be powerful enough to support all the stuff people need to do, like exec and fork, and heck, maybe even copy on write fork or memory mapping on disk files, but all in a kernel that has no idea about files or a file system, right? It needs to support exec, but with a kernel that knows nothing about files. We need the rest of the operating system somehow. Sure, the microkernel may be very simple, but now we're sort of requiring the development of some set of user level servers that implement the rest of the operating system. So we need that has to get done at least, and may require some just solving design puzzles. And finally, this arrangement requires a lot of chit chat over interprocessor communication, over IPC. So there's going to be great pressure to make the IPC very fast. So we're going to wonder whether IPC can be made fast enough to keep microkernels competitive. All right. And just in general, actually, not just IPC speed, but in general, there's a lot of reason to believe that monolithic kernels derive some performance out of the fact that they're integrated, that the file system code can talk to the virtual memory code and the memory allocation code, and it's all sort of one big happy giant program. And if you require all those things to be split out into separate servers, or maybe split between a kernel and user level, there may be fewer opportunities for optimization by way of integration, and that may or may not end up hurting performance. All right. So these are sort of cross-cutting, hoped for wins and sort of challenges that all the many microkernel projects faced. Because of today's paper, I'm going to tell you a bunch about L4 specifically, which is the microkernel that the authors of today's paper developed and used. L4 is not, certainly not the earliest microkernel ever made, but it's one of the sort of early microkernels that came out of all the work in this starting in the 1980s. And it's fairly representative as far as how it works. There's been, it's a bit of a moving target. It was a subject of intense development and evolution for many years, and it's still going strong. If you look it up on Wikipedia, you'll see that there's maybe 15 or 20 different variants of L4 that have kind of come and gone, and some are still here, starting, I think, in the late 1980s. And what I'm going to try to explain to you is my understanding of how L4 worked at about the time that today's paper came out. All right, so just at a high level, the L4 was certainly micro in the sense that it is a small kernel. It has only 7 system calls. Some of them are a little bit complex, but still it only has 7 system calls. Whereas today's Linux, the last time I counted, had in the mid 300s. And even XV6, which is an extremely simple kernel, even XV6 has 21 system calls. So L4 has only 7. So by that metric, it's simple. It's also not very big. I think as of the time this paper was written, it had about 13,000 lines of code, which is not too much. XV6 is smaller than that. I think XV6 is maybe 6,000 or 7,000 lines of code in the kernel. But still, XV6 is very simple as kernels go, and so L4 not much more complex than that. And this is, a 10th or a 20th or a 30th as big as Linux is. This is pretty small. It had only a few basic abstractions. It had a notion of what they call tasks or address spaces. And these more or less correspond to what we would call a process in Unix. It's a bunch of memories mapped starting at 0, and you're able to execute in here, just like in a process. One difference from XV6 is that there can be multiple threads per task. And L4 was in charge of scheduling the multiple threads of execution within each task. Part of the reason for this is just that it's very convenient to have threads as a program structuring tool. And it was also, I don't know if they actually supported multi-core or multiprocessor machines at the time the paper was written, but they may well have. And threads are, of course, just what you need to be able to harness multiple cores, executing in the same program. So where there were threads supported by the L4 kernel. So L4 supported tasks. It knew about tasks. It knew about threads, and it also knew about address spaces in the sense that you could tell L4, look, here's how I want pages mapped in my address space. And the other main thing that L4 knew about is interprocess communication. So there was every thread had an identifier, and one thread could say, look, I want to send a message, just some bytes, to another thread, and here's its identifier. Please please send a message to that other thread. So these are really the only task threads, address spaces, and IPC were really the only abstractions. The system calls, I don't know if I can be able to list them all, but the system calls were, there was a thread create system call, which also you gave it a address space ID and asked it to create a new thread. And if the address space or task didn't already exist, it would create a new task for you. So to sort of combine thread and task creation. There's send and receive, various flavors of send and receive, IPC system calls. There's a way to map pages into your or other address spaces. So you could ask the L4 to change the way your address space was set up, the way your page table mappings were set up. But you could also ask L4, if you had the right permissions, to go and change the way another task's address space was set up. And this was actually done through the IPC. You would spend through the IPC interface. You would send a kind of special IPC message that the kernel knew about to the target thread, and the kernel would modify the target thread's address space. And this is if you were creating a new thread. This is actually new threads are created with no memory at all. So if you want to create a thread, you first call the thread create system call to create the new thread and task and address space, and then you send it. You make one of these magic IPCs to send it some of your own memory, to map some of your own memory that you've prepared with instructions or data, to map that memory into the new task address space. And then you send a special start IPC to this new task with the program counter and the stack pointer you want it to start executing with. And then it'll start executing in that memory you've set up at the program counter that you asked it to start at. There's a way, not through system calls, in fact, I don't know how it worked, but privileged tasks could map device hardware, device control registers into their own address spaces. So L4 didn't really know much about devices like disks or network interface cards, but user level software could get directly at user level software that implemented device drivers at user level could get directly at device hardware. There was a way to, you could tell L4 to turn an interrupt, any interrupt from any device. L4 didn't really know which device, it just turned a given interrupt into an IPC message. So a device driver task could not just read and write the device hardware, but also tell L4, well, anytime that device interrupts, please send me an IPC message to notify me of the interrupt. And finally, one task could tell the kernel to give it notifications of another task's page faults. So if this task page faults, L4 would turn that into an IPC message and send it to another designated pager task. Send the notification of the page fault to a designated pager task. So every task had an associated pager task that handled its page faults. And that's the way you get hooks into the page faults in order to implement things like copy on write, fork, or lazy allocation. And that's it for the kernel. There's nothing else in L4. There's no file system. L4 didn't itself have support for things like fork or exec. It didn't have any communication beyond these very simple IPC, like didn't have pipes, didn't have device drivers, no networking support, nothing. Everything else, if you wanted it, you needed to supply as user level services. Okay, so one thing that L4 does supply is switching among threads. L4 would actually do the scheduling and context switches in order to multiplex a single CPU among multiple threads. And the way it did it, you would find completely unsurprising. L4 basically had saved registers for every task, for every thread. When it executed a thread, the execute thread, would jump into user space and switch page tables to that thread, and that thread would execute for a while in user space. Then maybe the timer interrupt would go off, and that was actually a device L4 knew about. The timer interrupt might go off after a while, interrupt into L4. L4 would save this task's user registers in a per task, an array of like tasks or thread structures, would save this thread's registers away. Pick a new task to run in a loop, much like the scheduling loop in XV6. Restore this task's registers out from its previously saved registers, switch page tables, and then jump into this task and execute it for a while until the timer interrupt went off, or until this task either yielded. I think there's also probably a yield system call or something like it. A task could yield the CPU, or a task could wait to receive an IPC. And in that case, L4 would jump back into L4, and L4 would save its registers, switch to a new task, and run that task. So that thread switching part of L4 is very, be very familiar. I mentioned this before, but I want to, because it comes up, I want to just write here this notion of a pager. To repeat, if a process takes a page fault, it traps into the kernel, and the kernel turns that page fault into an IPC message to a designated pager task and tells it the address, tells this pager task which thread faulted and the address it faulted on. And then the pager task, if it wants to say implement lazy allocation, maybe this thread read or write some memory that wasn't allocated yet, but it sort of asked to be lazily allocated. Its pager task would then be in charge of allocating some memory from L4, sending one of these special IPCs that cause the memory to be mapped into this task, and then setting an IPC to resume execution inside this thread. So there was this notion of pager task to implement all the stuff that XV6 or Linux implements in page fault handlers. Like you could implement copy on write fork with this if you liked, or memory mapped files, all using one of these pager tasks. So they were sort of powerful user level way to play tricks with driven by page faults. And so this is an example, one of many examples in which a microkernel like L4 might have been quite a bit more flexible for user programs than a conventional kernel. Like if you think Linux ought to do some extra thing, like maybe, if Linux didn't already have copy on write fork and you wanted to have copy on write fork, you really can't implement that in Linux without modifying the kernel. There's no way to write portable code, portable user level code for Linux that could implement something like copy on write fork. So that's not quite true, but it would be very difficult. Whereas in L4, it's relatively straightforward. L4 is like completely set up for you to be able to write user level code that gets the page faults that are required to drive copy on write fork, all in user space without having to mess with the kernel. Okay. So any questions so far about how L4 works?
Oh, sorry, can you just clarify the difference between a thread and a task?
Yes, a task corresponds to it's like a process. In XV6, it has a bunch of memory and an address space, and you can execute user code in it. XV6, if you have a process in XV6, there can only be one thread of control on a single, executing inside a process in XV6. But in modern operating systems and in L4, in a single process, in a single address space, you could have if you have multiple cores, you can have multiple cores executing in a single task. Each, typically, well, always each set up with its own stack inside that task's address space. And so if you That means you can, for example, write a single program that can get parallel speed up, improved performance from multi-core hardware by running one thread on, having multiple threads, each running on a different core, thereby getting more work done.
Okay, I see. Thank you.
Yes. Okay. So as you can see, this is a design that relies heavily on IPC, because you're going to want to talk to your file server. The file server is going to want to talk to the device driver server. You're going to have IPC messages flying back and forth for every system call, for every page fault, for every device interrupt. The IPC system just has to be fast. However, and now we're starting to sort of talk about a serious potential defect in the microkernel story. So first, let me show you a straightforward but very slow design for IPC patterned off of Unix pipes. And I'm bringing this up because some early microkernels worked in sort of a similar way to what I'm about to show you, which turned out to be slow. Okay, so let's suppose you have, you have two processes. We got P1. P1 wants to send a message to P2. So how should that actually work? Well, one possibility is to have a send system call, and you give send system call the ID of the thread you want to send the message to, and a pointer to the message, to the bytes maybe that you actually want to send to that process. So this is a system call, so you're going to jump into the kernel. Maybe we design this patterned after pipes in XV6, and so you can imagine there being a buffer of messages waiting. Maybe P2 is doing something else right now. Maybe it's a server, it's serving somebody else's request, so it's not ready to handle your request. You can imagine maybe a buffer of waiting messages in the kernel, like a pipe buffer. And when you call send, it appends your message to this buffer, waiting for P2 to receive it. Now, in fact, almost always in these systems, you rarely just wanted to send a message. You almost always wanted to get a response to. You wanted an RPC, or remote procedure call operation. So in fact, P1 would probably follow this immediately by a receive to try to get the response back. But in general, let's just imagine we're doing a one-way IPC for the moment. So send would append your message to the in-kernel buffer. It would have to copy the message bytes from user space into this buffer, and then return, and process one can do something else, like maybe prepare to receive the response. After a while, P2 is going to want to receive the next message. It's going to make the receive system call, and that's going to return the ID of the sender and copy the message into P2's memory. So it's going to take the front message off the queue, copy it into P2's memory, and then return. This is called, there's some words for this, whose opposites you'll see, and you saw in today's paper. This is called an asynchronous scheme, because P1 sends a message without having to wait for anything. It just appends it to this queue and returns. And it's called a buffered system because the kernel copies each message into the buffer, into its internal buffer on a send, and then later when the receive happens, it copies the message out of the buffer to the target. So this is asynchronous and buffered. If you're doing a full request response pair, then P1 is going to call send, send's going to return. P1 is then immediately, now let's assume, we're going to assume that there's really sort of two sets of buffers, one for each direction. P1's immediately going to call receive. Receive's going to need to wait for something to appear in the reply buffer. So it's going to have to yield the CPU. It's going to have to do something called sleep in XV6 to yield the CPU. And on a single CPU system, it may be only at this point that P1 gives up the CPU and now P2 can run. And indeed, on the hardware in this era was almost always single core. Certainly this paper is running on single core hardware. So P1's it's gonna be P1 executing and P1 not executing until P1 finally gives up the CPU and receive, waiting for a message to appear here. And only then will P2 be scheduled. Maybe it'll call receive. Receive will copy the message, and then P2 will make its call to send to append its reply. And then the send system call will return to P2. And at some point, presumably P2 will give up the CPU. Maybe the timer will go off. Then P1 will resume execution in the kernel, see that there's a message there, and return it back to user space. And so that means that in this design, this slow design, there's, in order to have a request and a response, there's 4 system calls, 2 sends, and 2 receives, and 8 user kernel crossings, each one of which is like reasonably expensive. There's a need to sleep. This receive has to sleep waiting for data to appear. And there's a full call to the scheduler loop and a context switch from P1 to P2 in order to make this. And each of these kernel crossings and context switchings is potentially expensive because every time you cross the kernel user boundary, you switch page tables, and that has a near certainty of disturbing the CPU caches. Like changing the page table probably flushes the TLB, the virtual memory lookup cache, which is going to slow things down. So this is a pretty slow way to go. It involves a lot of kernel crossings, message copying of messages between user and kernel, maybe allocation of buffers, etc. But it turns out that for this stylized case in which you're sending a request and you want to get a response back, you can strip this down to a considerably simpler design. And in fact, this is the way L4 worked. And this was laid out in a famous paper called Improving IPC by Kernel Design, published a few years before today's paper. So it does a couple things differently. For one thing, it's synchronous. That is, there's none of this. There's no dropping something off and returning and waiting, letting the other process pick up the data when it feels like it. Instead, send waits for receive and receive waits for send. So if I'm process 1 and I want to send and I call send, it doesn't copy my message into a buffer. It actually, P1 will now immediately, if the P1 send in the L4 kernel waits for P2 to call receive. And if P2 is already in the kernel waiting in a call to receive, well, P2 is either already in the kernel waiting in a call to receive, or P1 send waits for P2's next call to receive. When both have arrived here, when P1 is in the kernel and it's called to send, and P2 is in the kernel and it's called to receive, only then does anything happen. One reason this is fast is that if P2 is already in receive, then P1, when it's executing send in the kernel, can just, without a context switch or a general purpose scheduling, can just jump back into user space into P2 as if it was returning from this receive, right? And that's a much faster path through the kernel than, saving registers, giving up the CPU, calling the scheduler, and finding a new process to run. Instead, P1 send knows that there's a waiting receive and just sort of immediately jumps into P2 as if it was returning from receive. This scheme that they developed is also unbuffered. And it can do that partially because it's synchronous. When both the send and the receive are in the kernel, the message can be, sending some message. The kernel can directly copy the message from user space to user space without having to first copy it into the kernel and then back out of the kernel, because since both sides wait for the other system call to happen, that means that they've waited for both pointers to be known. Receive specifies where it wants the message to be deposited. So at this point, we know both addresses, then kernel can just do the copy directly instead of through the kernel. If the message is super small, like maybe only a few dozen bytes, then it can be passed in registers without any copy at all, what you might call zero copy. Remember, the send only proceeds if the P2 is already in receive, and the send basically jumps directly to P2. Well, this code path through the kernel takes care to not disturb a bunch of the registers. And that means that P1 can put its system call, if the message is short, it can put the message in certain designated registers. The kernel guarantees to preserve those registers on its way up to P2. And that means that when the kernel returns from the receive system call, but as a result of send, the contents of those designated registers hold the message, and therefore never had to be copied at all from memory to memory. Never had to be moved at all. They're just sitting right in the registers where they can be accessed very quickly. And this, of course, this only works for small messages. For very large messages, L4 could carry a page mapping in an IPC message. So for huge messages, like the result of reading a block from a file or something, you could just send the page and it would be mapped into the target's address space again without any copy. So this is done through page mapping. You give away the page or access to permission to share the page. And so small messages are fast. Huge messages are pretty fast. You still have to adjust the page table of the target, but that's much faster than copying. And a final trick that L4 played was noticing that if you're doing an RPC with a request and a response, there's a very stylized pairs of system calls, and you may as well combine system calls, send and receive system calls, in order to reduce kernel crossings. So for the special case of RPC, which is almost always what people are doing when they're using IPC, there was a call system call. And a call was basically a combined send plus receive, but without the return to user space and then re-entry into kernel space that a pair of system calls would take. And on the server side, there was a single call that would send the reply from one system call and then wait for the request message from anyone for the next system call. And this was basically a send of one response plus a wait to receive the next request. And this again cut in half the number of kernel crossings. And it turned out that the sum of all of these optimizations, for the kind of short RPCs, which are one typical workload, all this led to a 20x speed up. This is what their paper reported, 20x speed up over their previous system, which was presumably a little bit more like what I showed in the previous design. And so this was an impressive, this paper came out a few years before by some of the same authors, but a few years before the people were reading. And this caused people to view microkernels a little bit more favorably, that the IPC could actually be made quite fast. Any questions about these IPC tricks that L4 plays?
Yeah, I think I missed this, but when is a process sending or like receiving messages? Like when is it using that system call?
Okay, actually, so for RPCs, for request response, in fact, In fact, the processes use this pair of system calls rather than send and receive.
Okay.
So yeah, call, you really give it two arguments, a message you want to send and a place to put the response. And inside the kernel, it just combines these two. I mean, you could view this as a bit of a hack, but because IPC is so frequent, it's worth a little bit of hackery in order to make it be fast.
And in the diagram up there in the box where you have P2 sending that, or like running the receive system call, what prompted P2 to
Okay. In my RPC world, we have clients, and they're sending requests to servers, and the server is going to do something and reply. So since P2 is a server, we imagine that P2 is sitting in a while loop in which it's going to receive the next message from any client, do a little bit of work to process it, look up some data in a database or something, and then send a reply, then go back to the top of the loop and wait again. So to a first approximation, we expect P2 to spend all its time waiting for the next message from anyone, next request from anyone. And this design really, it does kind of rely on P2 always, when it's at rest, basically sitting in the kernel in a receive system call, waiting for the next request, so that the next request can directly basically return from that system call. Right? And that's the fast path that's super efficient in this design.
Cool, thank you.
Sorry, just to follow up on that, that means that you said that it goes from P1 and like returns to P2. So like to come back, you would need to send the response. So
that's right. We expect P2 to send a response, and that sending of the response actually follows basically the same code path in reverse, so that when P2 sends a response, that effectively causes P1 to return from. I mean, P1's actually making this system call. So the delivery of P2's response causes the return from this system call back into P1.
Okay, I see. Thank you.
This is a little bit different from the usual setup where you think of, you jump into the kernel in a system call and you execute that system call and it returns sort of all working on behalf of P1, which is the way pipe read and write work. Here, P1 is entering the kernel. It's P1 entering the kernel, but the return goes to P2. So it's kind of odd, but very fast. Okay. So this was a big sort of contribution to people taking microkernels, people's willingness to take microkernels seriously as potentially a replacement for monolithic kernels. However, you still leave open the question, even if RPC is fast, like where do you get the rest of the operating system? Right? This kernel only has like a few % of all the stuff like file systems and network stacks that we expect to be in a full operating system. What do we do about the rest? And this question is usually being asked in the context of some university research project with relatively limited resources. We need to get all those user level services from somewhere. Now, actually, there are specialized applications for which that's not too much of a problem. If we're, running a, some sort of device, controller, maybe the, ignition control system for your car that is, only running a few thousand lines of code anyway, maybe doesn't need a file system. Then we can get away with like very little stuff at user level, and microkernels totally make sense for that kind of application. But the people, in these projects, really, they had ambitions that, oh gosh, we're going to totally replace existing operating systems, and they hoped that they could build something that people would want to run on their workstations and run on their servers and everywhere, and just replace big monolithic kernels altogether. But for that, you need all the stuff that an operating system does. One possibility, the most maybe sort of philosophically consistent possibility, would be to re-implement everything you need, but in a sort of microkernel way as lots and lots of different user level processes. But that's just actually people, there were projects that did that, but it's a vast amount of work. And more specifically, people really want to run, in order for me to use a laptop, it just has to run Emacs, right? And it has to run my favorite C compiler. Otherwise, I'm just definitely not going to switch to your operating system. And what that meant is that microkernels, in order to gain any kind of adoption, they had to be able to support existing applications. They had to be able to be compatible, provide a identical, at least at the system call, at the higher level service API level, they had to be totally compatible with some existing operating system like Unix, like Linux, in order for anybody to be willing to switch. So these projects faced a more specific problem of how they were going to get, how are they going to attain compatibility with existing applications written for Linux or maybe Windows or something. But for this project, it was Linux. And rather than write their own totally new set of user level servers that mimicked Linux, they decided to take the far easier path, and many projects did this, of simply directly running an existing monolithic kernel as on top of their microkernel instead of re-implementing some new thing. And so that's exactly what today's paper is about. It has indeed, L4 microkernel down at the bottom, but also as like a pretty big server, they run a pretty full Linux kernel as a user level process. And so that may sound a little surprising. The kernel is not a user level process, right? The kernel is the kernel. You think of it as running on the hardware. But in fact, the Linux kernel, as you can see from running XV6 and QEMU, which is running in user space after all, a kernel is just a program. And so with some modifications, it can be made to run at user level. And so they had to modify Linux, and they took a lot of the low-level stuff in Linux. For example, the code in Linux that expects to be able to directly modify page tables or read and write processor registers. There was some low-level stuff they had to modify. So some parts of Linux they had to change in order to convert them to basically make system calls or send IPC messages through L4 instead of directly get at hardware. But for the most part, they were able to directly run without change almost all of Linux. So that means they got as part of Linux, a file system and a network support and all kinds of device drivers and who knows what that comes with Linux without having to write their own version of this. Now, in fact, the way this was set up was that the Linux kernel ran as one L4 task, but each Linux process ran as a separate L4 task. So when you log into this Linux and you ask it to run a shell for you, or a terminal window or something, it's going to fire up an L4 task that's going to run that Linux program at user level. So there were one task for Linux and one task for each Linux process that you fire up under Linux. And Linux, instead of directly, modifying the page table that the VI process uses, Linux is going to send the right IPCs to L4 to cause L4 to change VI's page table. Any questions about the basic scheme here? Another thing that was changed, many small things were changed, but a specific thing of interest is that when VI wants to make a system call, so if VI doesn't know it's running on L4, in this scheme, it's really, all these programs just think of themselves as running on Linux. When VI wants to make a system call, L4 does not support. It's not making an L4 system call, it's making a Linux system call. So VI system calls like fork, there's a little library basically that was linked into these Linux processes that would turn calls to things like fork or exec or pipe or read or write into IPC messages that it would send to the Linux task and wait for the response to the Linux task and then return as if the system call had returned. So these little libraries would turn system calls into IPC messages to Linux. And what that meant is that if the Linux kernel task isn't doing anything else, it's sitting in a call to receive, waiting for the next system call request IPC from any one of these processes. And that led to that leads to a significant difference between how this Linux works and how ordinary Linux works. In ordinary Linux, just like xv6, there's basically a kernel thread that corresponds to every user level process. And when a program makes a system call, the kernel runs a thread on behalf of that system call. And in ordinary Linux, when Linux switches between kernel threads, that basically implies a switch from one process to another. So there's kind of one-to-one correspondence between what kernel thread Linux kernel is running and what process is going to run when Linux is done. Here, that connection is broken. There were indeed, in this Linux server, a kernel thread corresponding to each. I'm sorry, let me start again. The Linux kernel server was running in a single L4 thread. So there was only a single sort of thread of control executing in Linux at a time. However, just as in xv6, this one thread of control would switch, using a technique very much like xv6's context switch, could switch between a kernel thread corresponding to each user process. However, which of these kernel threads were implemented purely within Linux, had nothing to do with L4 threads. There's only one L4 thread here. But which user process was running was determined by L4. So in this setup, Linux might be serving a request from executing the kernel thread for VI, serving a VI system call, at the same time that L4 is causing this shell to run in user space, which is very unlike what happens in xv6 or Linux, where there's a direct correspondence between the sort of active kernel thread and the corresponding user level thread. Here, L4 is off running whatever it feels like. And these threads in the Linux kernel are really much more private and are just about Linux being able to concurrently execute system calls in different stages of execution, where maybe one process is waiting for the disk in its thread. Linux can run a different process's kernel thread to serve that process's system call. So you might wonder why this design didn't directly use L4 threads to implement the various different kernel threads inside Linux. Why did Linux implement its own sort of internal threads package instead of using L4 threads? And the answer was that in those days, they didn't have access to multi-core hardware. They were using single core hardware. So there was no performance advantage to being able to execute multiple threads in the kernel at the same time, because there was only one core. So a second thread couldn't be executing. Only one thread could execute at a time due to the hardware. And the other, maybe even more powerful reason is that in those days, the version of Linux they were using did not have the support that's required to have multiple threads, multiple cores executing inside the kernel at the same time. They were using a uniprocessor Linux. It's an old enough Linux that it expected only one core in the kernel at a time. It didn't have things like the spin locks that xv6 has that would allow it to correctly execute multiple cores inside the kernel. So there would have been no performance advantage in having multiple L4 threads active inside the kernel, but it would have required adding in, for no performance win, adding in all the spin locks and other stuff that's required to support concurrency. So they didn't do it. a drawback of this arrangement is that in ordinary Linux, in native Linux, like you would run directly on your laptop, Linux has a lot of sophisticated scheduling machinery that can do things like impose priorities on different processes or ensure various kinds of fairness. And that works fine because on your laptop, because Linux is in control of what process is running on each core. But in this setup, Linux is not controlling that at all. Linux has no control over what process is running because it's L4 that does this scheduling, not Linux. These processes are scheduled by L4, so they kind of lost the ability to have Linux be in charge of scheduling. That's a bit of a defect of this, although I'm sure later versions of L4 had some way for Linux or something like it to be able to tell the L4 scheduler, oh, look, please give this process higher priority or whatever. Still, it's a bit awkward. All right. So they went to all this work to get this going. And you should ask yourself, what's the takeaway lesson from this paper about microkernels? Now, one thing so for us, this paper has a lot of interesting tidbits about how microkernels work and about how Linux works and how, you set up, how you can design a system like this, which may be interesting. But in the larger world, people want to draw some lessons. They need to be able to present some lessons in this paper. The paper is not really answering the question, are microkernels a good idea? That's not really what's going on here. What the paper is part of an argument about whether microkernels have enough performance to be worth using. And the reason is that in maybe sort of 5 years or 5 or 10 years before this paper came out, there was a famous set of measurements on one of the predecessor microkernels, an earlier microkernel called Mach, basically running in very much this configuration, but a different, totally different design internally, but kind of the same architecture. The name of this earlier microkernel project is Mach. There was measurements on Mach that showed that Mach was dramatically slower than just ordinary Unix when it was run in this configuration. And there were a lot of reasons for that, having to do with the IPC system not being as optimized as you might hope. There being just sort of more context switches and user kernel crossings and cache misses and whatever. There's a whole lot of reasons why Mach was slow, but many people saw those benchmark results showing that Mach was much slower than native operating systems and decided that microkernels were just hopelessly inefficient, were unlikely ever to be fast enough to be competitive, and we should just all use monolithic kernels. Today's paper is like an answer, basically, to that argument. It's sort of the rebuttal to that argument. And the point of this paper is to show that you can build this architecture, and if you pay enough attention to optimizing performance, you can get competitive performance with native operating systems. So it's just directly running Unix. And therefore, you can't dismiss microkernels simply on the basis of performance. You may not want them for other reasons, but you can't use performance as the reason to reject them. A huge part of the ingredient in making that argument is that they made the IPC much faster with the techniques that I outlined a few minutes ago. And you can see this, I think, in a very simple benchmark in Table 2, if you have a copy of the paper with you. Table 2 has measurements of just native Linux running in the ordinary way on hardware. And on native Linux, they show that, on their hardware and their version of Linux, that a single simple system call getPID took 1.7 microseconds. And they also show that the sort of equivalent thing in L4 setup, where you have to send an IPC request and get an IPC response just for this get process ID system call, that took 4 microseconds under L4 Linux, which is to say twice as long, but there's sort of twice as much work going on because you're doing 2 sets of user kernel crossings instead of just a single simple system call. That is, they could claim that they had pared the expense of these IPC-based system calls down to basically the minimum, that is, twice the cost of a system call in native Linux, and therefore they were doing roughly as good as you could possibly expect. Now, of course, that's still, their system calls are still half as fast as native Linux. And it's not clear unless you did some measurements whether system calls taking twice or simple system calls taking twice as long is a disaster or not a problem. And in order to show that, and it might be a disaster if you do a lot of system calls, or it might be not a problem if you do relatively few system calls, or there's a lot of work per system call because maybe your system calls are more complicated than get PID. And their answer to that in the paper is the figure-8 benchmark using this benchmark called AIM, which is just it's a benchmark that does all kinds of different system calls. It reads and writes files and creates processes, sort of does all the things with the kernel that processes do. And they basically showed in figure-8 that their setup running a much more full application that does much more than just get PID runs only a few % slower than native Linux. And that therefore, hopefully you could expect that whatever it is you wanted to run on a computer would run almost as fast under L4 plus Linux as it does under a straight operating system, under native operating system. Therefore, they were basically, to a first approximation, as fast as just running straight Linux, and therefore you should take them seriously. Okay, so that was an impressive result, by the way. This is like somewhat unexpected and cool. Just fast forwarding 20 years, where this ended up. As I mentioned before, people actually use L4 in a bunch of embedded situations. Particularly, it's used a lot. There's many instances of L4 running in smartphones, hidden from view, but nevertheless, all running various kinds of custom software, not running. They don't have to have compatibility with Unix in these situations. Microkernels in other more general situations like workstations or servers never really caught on. And it's not because there's necessarily anything wrong with that design. It's just they would have to, in order to displace some existing software, your new thing has to be, better so people will be motivated to switch. And these microkernels were perfectly good, not certainly elegant, but it was hard for people to put their finger on why it was so much better that they should go to the trouble of switching from Linux or whatever they were running to this. And so it never really caught on, not necessarily for good reasons, but because they weren't dramatically better. On the other hand, many ideas from this architecture had a lasting impact. People had to work out much more interesting and flexible ways of using virtual memory in order to support operating systems on their microkernels. And those more sophisticated interfaces made their way through things like mmap into mainstream operating systems like Linux. This idea of running an operating system kind of on top as a server on top of a lower level operating system is extremely popular today in the form of virtual machine monitors, which are used all over the place in sort of cloud hosting services. The desire for extensibility, you could modify a user level service. The way that played out in things like Linux was loadable kernel modules, which allow you to modify the way the Linux kernel works on the fly. And of course, the sort of client server, good support for this client server architecture also made its way into kernels like macOS, which has good IPC and good client server. And that's all I have to say for this lecture. But I'm happy to stick around for questions. Thank you.
Thank you.
You're welcome.
Oh, I wanted to ask, so the paper was talking about virtual, about page tables at, I think, 4.2. And it was saying how I think it was kind of what you mentioned before, where you said that there is a wrong way to do that. I think might be kind of similar to that, but if you do this thing that you explained in this in your picture now, would it be, I guess, how would the page tables work in this case?
Well, are you, you may be referring to section 4.3, the dual space mistake.
Oh yes, sorry, 4.3.
Oh no, yeah, that's a bit of a complicated story, but the let's see. The part of the background is the way that Linux worked in those days, and indeed until recently, is that when you're running at user level, the page table that's active has both the processes pages, user level pages mapped in, and all of the kernel mapped into that one page table on the x86 anyway. So when you made a system call and jumped into the kernel was already mapped into the page table, and therefore no page table switch was required. So when you make a system call, it's that much more expensive and much more cheaper because there was no page table switch. If you're calling XV6, the trampoline code switches page tables, which is an expensive thing to do because it flushes the TLB cache of virtual to physical mappings. Anyway, so for efficiency, Linux used to map kernel and user space in the same page table and had fast system calls as a result. So they, for reasons that aren't very clear, decided to do this same thing, to set up the mappings in the Unix server. Well, what they wanted was that when a process sent a system call over here, they wanted to have the page table that was active while in the Linux server while processing that system call include all the virtual memory mappings for the process that sent the system call. And that at least would make it simpler to look up virtual addresses passed as system call arguments, like pass to read. The reason why this worked out poorly, there were a bunch of reasons. One is that L4, which doesn't know anything about any of this stuff, L4 just knows there's two processes. And so when you send an IPC from one process to another, L4 just switches page tables. It always just switches page tables. This guy had a page table, the VI had a page table. L4 associates a page table with the Linux kernel. It just always switches page tables. So you couldn't even, due to L4, due to the different ways system calls were implemented and the fact that L4 was involved, there was no way to preserve the page table during a system call. That just wasn't possible because L4 always switched page tables when it switched from one process to another. So they were never going to get the efficiency win of not having to switch page tables when sort of crossing from user to kernel. But I think they wanted the convenience of being able to directly use user-supplied virtual addresses, but that meant that the mappings they needed to be active depended on which process they were executing a system call on behalf of. So there couldn't be any one page table for Linux. They would have, the page table Linux server wanted to use depend on what process it sent the system call RPC, but L4 did not know how to play that game. L4 associated a single page table with each process, with each task. And so and it would just switch to that page table. So tough luck. Linux didn't have any way to cause the page table to differ depending on who had sent the system call. In order to deal with that, apparently they made a bunch of shared memory copies of the kernel, one for each process. And so each of these shared memory copies of the kernel had all of the kernel memory mapped into it. So they were all the same kernel data structures, but each process had a dedicated kernel task associated with it. And therefore that basically allowed them to trick L4 into switching to the appropriate page table that included that process plus the kernel, depending on which process sent the system call request. And, I think that kind of worked, or I don't know, forget what they said, that worked, but it was slow or something. Because there were a lot of tasks. Anyway, it's like a complicated story, and I think it didn't work out very well for them.
Okay. Okay, I see. I think that explains well why this thing is harder to do than what we do in XV6. Okay.
Yeah, this because there's not. Yeah, this picture in XV6 or even standard Linux is much simpler than this because you're just jumping directly into the kernel, and the kernel has direct control over all the paging hardware, which it doesn't have when it runs on 04.
Right. Okay, I see. Thank you. Thank you.
I was gonna ask why it seems like some tasks are more appropriate to be put outside the kernel than others. But this like the approach with microkernels always seems to be either everything or nothing, or like either you have a monolithic kernel doing everything or nothing. Just like I feel like paging and some other things could be very efficient inside the kernel, and then maybe like file systems, that things that need to be swappable could be outside. And then even like you could maybe even have a kernel that has some functionality, but you can opt to not use it and provide your own. Is there any?
Everything you say is absolutely well taken, and indeed there were a lot of microkernel or microkernel related projects, and many of them built various kinds of hybrids. Like there were actually a couple different versions of Mach, and some of them were sort of hybrid kernels in which, yeah, there was this microkernel that knew about IPC, but also in the kernel was a complete Unix. So for instance, Mach 2.5 was this hybrid with a microkernel and Unix all sort of in the same kernel. And you could make system calls to either, and some stuff was built in the sort of microkernel-y way, but some things they would just use the kernel that was in Mach, that was built into the Mach kernel. The Unix kernel that was built into the Mach kernel. And modern, Mac OS also is built in a way that, like the way you describe, Mac OS has a complete operating system with a file system and everything inside it, but it also has good support for IPC and sort of like threads, all the stuff you would want to build microkernel style services.
I think Google's Fuchsia, I'm aware of, also implements some of these ideas now as well.
Oh, I'll bet, yeah. So anyway, there's no one way. There were people who were sort of hoping that a very pure scheme could be made to work. But it was not the only possible way forward.
All right, thanks. Got to run to my lecture, but I'll see you guys.
See you later.
Thank you.
You're welcome.
Oh, I didn't have I have just a remark. I think it's fascinating that it's like 5% slower, but it does so much more work. Yeah, I was fascinated by that.
You mean that even though it's doing much more work, it's only slightly slower?
Yeah.
Well, they really sweat blood over the IPC performance. Yeah. And it's another thing to remember, of course, is that if you're doing significant amount of work per system call, like, looking at files and directories or something, then the cost of the system call or the IPC itself starts to be less important. So the combination of faster system calls plus real programs do things other than making system calls.
But you would also like switch page tables and the other stuff.
Yeah, although the paper, I did not talk about it, but the paper had some clever tricks for avoiding the cost of switching page tables. I don't know if you remember, there's some, it's like on page 6, we're talking about supporting tagged TOBs or small spaces. They had some clever ideas for not having switch page tables, which I had not heard of before I read this paper. So.
This is pretty cool. Thank you so much.
Yes.
Bye.
Bye-bye.